Good day, students. Welcome to part one on volumes of solids of revolution and on cross-section. We're going to be taking the approach of disk and washers to determine the volume of regions that are generated as a result of rotation. Okay? All right, so let's start by taking a look at the formulas first, and then we will apply the formula to an example, okay? So we're going to divide this formulaic determination process into two areas. We'll look at solids of revolution first, and then we'll do cross-section, volume of cross-sections second, okay? So let's write this down, solids of revolution. All right, so what we are going to be looking at is a situation where um, we're going to be rotating this region right here. Let's call it R. This region bounded by these two curves. We're going to be rotating this region around some lines, okay? So let's start off by rotating um, this region around the line y equals m, all right? So rotate about y equals m, but there's a special condition here where um, m is basically going to be beneath both functions, okay? So f of x is going to be greater than g of x. As you can see here, f of x, the green one is on top of g of x, and g of x is going to be greater than our axis of rotation, y equals m. All right, so let's go ahead and label our function so we know what's going on. The function on the top is f of x, and the function on the bottom, this function right here, this is g of x. Okay, so our axis of rotation, let's go ahead and draw that. Let's move it right into view. So let's say somewhere beneath, it could be anywhere as long as it's beneath both of the two functions. So let's just place it right here. Okay, and let's label here, this is basically m, an arbitrary m. The equation of this line is going to be y equals m, consequently, okay? So let's say that the point of intersection for this region is A to B, okay? So what will our volume, the volume of the resultant solid when this region is rotated about this axis going to be? So you just visualize this region right here being rotated about this axis, okay? So you're going to have a circular region right here with a big hole in the center. So the volume of that resultant solid, a volume, is going to be the integral from A to B of, we're going to be finding the infinite sum of a washer, or the difference between the areas of two disks. Okay, so we're going to have an outer disk, which is the disk created by this outer function going around, and this inner disk. So we're going to be summing we're going to be finding the infinite sum of the difference in the areas of the two disks. Okay, so think about it this way: you have the green one forming a big disk on the outside, and then the blue function forming the disk on the inside, and then the difference in the areas is going to be this region right here. Okay, so it's going to be a tiny slice of disk, but we're going to be looking for the infinite sum of those tiny slices. Okay, this is just one slice of that disk right there. And as you can clearly see, this is a dx measure. All right, so let me also go ahead and label my axis so we don't get this all mixed up. This is my x-axis, you already know, and this is my y-axis. Okay, so this slice is a dx slice. So imagine this is going to be like a washer. Okay, all right, now so the formula for the area, I'm sorry, for the volume, is going to be the integral of the difference of the area between the two disks. So pi r squared. So pi, we can factor out pi because it will be a common expression, common term on both area expressions. Okay, so pi times big R sub 0 square. Let me change the color of that. This, well, it's okay. Let's just use that. Okay, so big R sub 0 square. This is known as the outer radius. Okay, so pi R, big R sub 0 square is the area of the outer disk. Okay, minus little r sub I square. So pi times r sub I square is the area of the inner disk. So this blue area here is going to be r sub I square. Pi r sub I square, and then this bigger area will be pi big R sub 0 square. Okay, so that's the area. So we know that the formula for volume is area of the base times what? Times the height. So the thickness of the disk is dx. Okay, so this expression is a general formula for um, the area of a washer. Okay, so let's just make a note here on the side that r sub 0 is outer radius. Okay, r sub 0 is outer radius, and little r sub I is inner radius. So let's keep that in mind. Okay, so this is a general formula. Let's apply it to this particular situation here, where you have a function on top, a function underneath, and then the axis of rotation beneath both functions. So your volume is going to be what? It's going to be the integral from a to b. Notice the limits of integration from a to b is going in the direction that this dx is going. Pi times, now what is the length of our outer radius? Let's make this quickly bracket. Our outer radius is going to be the length from this function to this line right here. So it's simply, since the function is on top, it's simply going to be let's write it, function f of x minus the axis of rotation m. So that expression is our radius. Okay, but since m is beneath here, this minus will change into a plus, and then it becomes a plus here. But this is how you write it. So f of x minus m square. So this entire expression, f of x minus m, is the length of the outer radius. If we're rotating about our x-axis, guess what? This m will basically drop off, and in that case, we're going to be rotating around the x-axis. All right. So this is the outer radius minus now the inner radius. Can you imagine what that is going to be? Similar process is going to be the function that's the inner function, or the function closer to the axis of rotation. This what is it? This g of x minus the axis of rotation, which is m, quantity square. So this is the inner radius, okay? And then that entire expression multiplied by dx. All right, so let me just give you a segment representation here. So from here to here, that's the outer radius, and then from here to here, that's the inner radius. Okay, so outer radius, inner radius, and then there goes the expression for your the resulting volume when this segment is rotated about this line. So this is a washer. Okay, is a washer because you have a big hole in the center, just like a donut, because of this g of x piece. If g of x were non-existent, guess what? It's existent. Then guess what? We're going to have a disk. What does that mean? Well, if we didn't have a function down here, what we'll have is a solid with no hole in the center. So it's going to be a disk. In that case, this entire portion of our integral expression will be gone. Okay? And all you'll be left with is this piece right here for the determination of our volume. That's if there wasn't any function on that underneath. Okay, so washer is if you have two functions bounding a region, and then disk is what you have when you just have only one function and an axis of rotation. All right. Um, Another point to note is that if our axis of rotation were the x-axis, this m's we see here will drop off. Okay, and you just be left with f of x squared and g of x squared. All right, now let's consider the case. What if our axis of rotation were both the two functions? Okay, what would that situation be like? So in that case, what if we're going to rotate about um, y equals n, where if y equals n is above all of them, we're going to have a situation where n is going to be greater than f of x, and f of x will be greater than g of x. All right. So what would the area formula be in that case? Well, let me show you where that line is. So the line that we're talking about right now is above both functions, anywhere above both functions, okay? So let's go ahead and put it somewhere here. So how about, what if it's somewhere here, okay? So that's our line, and put it there. Okay, that's our line, y equals n, all right? What will happen if, what will be the expression of the volume when this region is rotated about this new axis with equation y equals n? It's going to be very similar. Only thing that's going to happen is that there's going to be a switch. These functions, the position of these two functions will switch around, and the order of the expressions in there will also switch around. Okay, so let's write down the area, the formula first, and then see if we can make sense, get a conceptual understanding as to why it is the way it is. All right, so the volume is going to be the integral from a to b of pi times the outer radius square minus the inner radius square dx. Okay, this is the formula, standard formula for source of revolution. Okay, so now let's apply this formula to this situation we're talking about here. So we're going to be having the integral, let's try that again, the integral from a to b of pi. Now, what is our outer radius going to be? If you look at this function right here, our outer radius is going to be what you get when you subtract this entire length from this function right here. Okay, so this is going to be the outer radius. Let me indicate it for you with a line so you can see what the outer radius is. This would be our outer radius right here. Okay, so basically you'll be subtracting n, which is the entire length from here to here. You're going to be subtracting it from, subtracting g. G is, take that out. G is this piece right here. Okay, that's g. So when I subtract g from subtract g from n, that will give me the outer radius right there. Okay, so let's go ahead and write down what that looks like. That's going to look like, let's see, it's going to be n, because n is the bigger one out of the two. Okay, n minus g of x quantity square. Let me color code it so we can match it. So n minus g of x quantity square. All right, so what did we just create? We just found the outer radius. Okay, the outer radius, that's from here, the distance from here to here. Okay, that length, that's what we just found. Now I'm going to find the inner radius. To find the inner radius, this is what we're looking for right here. Let me go ahead and show you. So the inner radius is going to be this piece. How do you find the inner radius? You basically look at the entire length, which is going from here to here, and you subtract the value of f from there. Okay, so if I subtract f from the entire thing, that gives me the inner radius. All right, so what would that expression look like? Let's go ahead and write it down. The expression is going to be, we're looking for the inner radius, r sub I, and then we're going to be squaring it. So minus, um, let's see, n again, n minus the function that's closer to the axis of rotation, the inner function is f of x. All right, so that's the inner radius quantity square. Okay, so just remember, all we're doing is the basic area of a circle. Remember, the area of a circle is pi r squared, right? But our r is a little bit complicated here. It's just determined by computing the difference of functions. Okay, so this dx is basically what's the expression for the volume of a region rotated about a line that's above both functions is given by. All right, so that goes the formulas you want to have mastered in order to be able to determine the volume due to solids of revolution. Okay, so that was the first formula you need to know. And the second formula is right here that you need to know. That's this one. Okay? And then when you have disc and washers, when you have washers, that's a special case of these formulas. And also when you rotate about an axis, there's a special case of these formulas. If you are doing a vertical horizontal rotation about the y-axis, all these x's become y's, basically, and your limits become y's, and you have dy instead of dx. All right, so that's that.